Good morning, everyone. Welcome back to the next lecture. Today, we will continue our discussion on input output analysis. In the last lecture, we discussed some problems related to the two sector and three sector model as well. So, we will continue our discussion by taking some more problems related to the three industry models. See, consider one example. We have the given problem. Let us consider an economy with three sectors. We have a primary, secondary and tertiary producing sectors are there. And the flow of output for the intermediate use and the final demand is indicated in the following table. So table I am showing here. And we want to find out the new sectoral output if the final demand is increased to 400, 500 and 350 respectively. Earlier our final demand was, see in the given input output table, it is 300, it was 393, 479 and 320. Now the final demand is increased to 400, 500 and 350. So here the inter-industry demand is given, that is primary sector, secondary sector and tertiary sector. We have a three industry model. First we are going to frame, that is the coefficient matrix. So coefficient matrix we can frame by taking the first row, then divide with 700. Then the second row divide with the 800. Then consider the third row and divide with the 600. So it will become, see I am denoting here matrix A, which is the coefficient matrix, 35 divided by 700, 105 divided by 700, 70 divided by 700. Then the second row will become 200 divided by 800, 96 divided by 800, 120 divided by 800. Similarly, the third row, that is 72 divided by 600, 120 divided by 600, 900 divided by, 90 divided by 600. So we are going to simplify it by dividing the each element here. So it will become, so here the coefficient matrix A is equal to 35 divided by 700, which is equal to 0.05. Then 200 divided by 800, which is equal to 0.25, 0.12, 0.15, 0.12, 0.20, 0.10, 0.15 and 0.15. So this is the coefficient matrix. See, we have the final demand vector, which is, so now we are going to simplify the, each and every element. See here 35 divided by 700, which is equal to 0.05. Then 105 divided by 700, which is equal to 0.15. 70 divided by 700, which is equal to 0.10. Similarly, other elements can also do. We will get 0.25, 0.12, 0.212, 0.20, 0.15 and 0.15. We have a 3 by 3 matrix. So we can say that it is three industry model. And the final demand vector, that is 400, 500 and 350. That means we want to find out new sectoral output if the final demand is increased to 400, 500 and 350. So I am considering here the final demand vector, that is 400, 500 and 350. Now after finding the matrix A, we are going to consider, see the difference between the identity matrix and the coefficient matrix. So I am introducing here the identity matrix here, that is 100, 010, 001. We have a 3 by 3 identity matrix as well, because we have 3 by 3 coefficient matrix. So we can subtract the coefficient matrix, the elements in the coefficient matrix from the identity matrix. Then it will become, see it is 0.95 minus 0.25 minus 0.12 minus 0.15, 0.88 minus 0.20 minus 0.10 minus 0.15 and 0.85. So this is the matrix. See here all the diagonal elements are positive, 0.95, 0.88, 0.85. This is the one of the most important condition for Hawking-Simon. See, Hawking-Simon condition says that we have to satisfy the both condition, and the first condition is, that is main diagonal elements are positive. So the first condition is satisfied. Now we are going to find the determinant value. So the determinant value, if you go for considering the determinant value here, then the first element, that is 0.95, by crossing the first column and the first row, then what is remaining here? It is 0.88 into 0.85, which is equal to 0.748, then minus 0.20 into minus 0.15, which is equal to 0.03. Then minus 0.25, so it will become plus 0.25. Then crossing the second column and the first row, minus 0.15 into 0.85, which is equal to minus 0.1275. Then minus 0.20 into minus 10, which is equal to minus 0.02. Then here the third element, it is minus, so it is minus 0.12 into crossing the first row and the third column. See, we will have minus 0.15 into minus 0.15, it will become 0.0225, then minus here also, so it will become plus here, 0.88 into 0.10, which is equal to 0.0888. So if you go for simplifying it, then we will get the determinant value, and the determinant value here, it is equal to 0.6319. See, our second condition is also satisfied. What is the second condition? The second condition says that the determinant value should be greater than 0. It is positive. Determinant value should be positive, that is non-singular. So the first condition, that is all the diagonal elements are positive and also the determinant value is greater than 0. So we can say that Hawking-Simon conditions are satisfied. We can find the inverse of matrix and the solution will always exist. So after finding the determinant value, we can go for finding the inverse. So for that, we have to find the minors and cofactors, then cofactor matrix, and then adjoint matrix. Then we can go for finding the inverse. So first we are going to consider the minors. So the minors for the each element we want to calculate. So first element here it is 0.95. The minor of the first element by crossing the first column and the first row, then if you go for multiplying 0.88 into 0.85, which is equal to 0.748 minus 0.20 into minus 0.15, which is equal to 0.03. So if you go for taking the difference between these two numbers, then it will become 0.7180. So this is the first minor. Similarly, you can find the second minor, third minor, fourth, fifth, sixth, seventh, eighth and ninth. We have a 3 by 3 matrix, so we will have a 9 minors as well. So the 9 minors are found. Then after finding the 9 minors, we can go for calculating the cofactors. So for the corresponding to the first minor, we will have the first cofactor, which is equal to minus 1 raised to the power 1 plus 1 into the first minor, that is equal to 0.7180. So it is minus 1 square, which is equal to 1 into 0.7180, which is equal to plus 7180. The second minor, that is minus 1 raised to the power 1 plus 2, that is minus 1 cube. So minus 1 into minus 0.1475, it will become minus will become plus, so it is 0.1475. Similarly, we want to find out the third cofactor C13, which is minus 1 raised to the power 1 plus 3. So it is minus 1 raised to the power 4, that will become 1 into 0.1105, which is equal to it is plus 1 into plus 0.1105, which is equal to plus 1105. Similarly, you can find C21, C22, C23, C31, C32 and C33. We will have all the cofactors we are calculated here, and I am writing all the cofactors separately here. We have 9 cofactors as well because we have a 3 by 3 matrix. After finding the 9 cofactors as well, we can go for calculating, cofactor matrix by replacing the elements in the original matrix by using the cofactor elements. Then it will become, cofactors we are replacing here with 0.7180, 0.1475, 0.1105, 0.2305, 0.7955, 0.1675, 0.1556, 0.2080, 0.7985. This is the cofactor. See, after finding the cofactor, we can go for calculating the adjoint matrix. See, adjoint matrix we can find by taking the transpose of cofactor matrix. Here we are going to interchange rows into columns. So first row now will become the first column here. The second row will become the second column here. And the third row will become the third column here. So we are calculated here the adjoint of a given matrix. And after finding the adjoint, we can calculate, the inverse matrix. So inverse here, it is adjoint divided by the determinant value. So it is separately we are writing here 1 by the determinant value, which is equal to 0.631, which we are already calculated, and multiplied with the adjoint matrix. So adjoint matrix we have here. So here we are going to multiply this inverse into the matrix D. That is, first I am considering here the order final demand vector. See, this was the order final demand vector, that is 393, 479 and 320. After calculating the order one, we will go for calculating the changed final demand also. So here, by considering the final demand vector as 393, 479 and 320, we are going to multiply here the first, this particular adjoint matrix, that is 3 by 3 matrix, with the vector, final demand vector, that is 3 by 1 order. So we have a 3 into 3 matrix and 3 into 1 matrix. Of course, the matrix multiplication is possible. And if you go for multiplying these through matrices, then you will get a 3 by 1 matrix. So here multiplying the first row with the concerned column vector. So here it will become, see, if you go for multiplying 0.7180 into 393, it will become 28.17 plus 0.2305 into 479, which will become 110 into 41. Then the third element, that is 0.1556 multiplied with 320, it will become plus 49.79. Then the second row we are going to multiply again with the column vector here. 0.1475 into 393, it will become 57.97 plus the second element, that is 0.7955 into 479, which is equal to 381.04 plus the third element, that is 0.2080 into 320, which is equal to 66.56. Similarly, we are also going to multiply the third row with the final demand vector, then it is equal to 43.43 plus 80.23 plus 255.52. So if you go for simplify it, then it will become, if you go for adding all these elements, then it will become 28.17 plus 110.41 plus 49.79, which is equal to 442.37. Similarly, if you go for adding up the second row, then it will become 505.57. Then similarly, if you go for adding each element in the third row, then it will become 379.18. Then each element in this row vector we are going to divide with, or we are going to multiply each element by 1 by 0.6319. Then it will produce, see, 700, 800 and 600, which is the final output of the industry 1, the second industry and the third industry. So now we are going to find out, see, this is the x1 is equal to 700, x2 is equal to 800 and x3 is equal to 600. Now we are going to find the new output or new sectorial output if the final demand is increased to 400, 500 and 350 respectively in the industry 1, 2 and 3. So here, by considering the inverse, that is 1 by the determinant value into this is the adjoint matrix, then multiplied now with the final demand vector. See here, the final demand vector, now I am considering the new final demand vector, that is how much it is increased to 400, 500 and 350. So I am considering directly here the new final demand. So the final demand vector is equal to 400, 500 and 350. Now if you go for multiplying these three matrices, here two matrices, then it will become, see, it is first row I am going to multiply with the final demand vector. So it will be 0.7180 into 400 plus 0.2305 into 500 plus 0.1556 into 350. So I am writing here. Similarly, the second row will be multiplied with the final demand vector, and the third row is also multiplied with the final demand vector here. So this will become just like what I have written here. This will be the same. So now I am going to multiply, see, 1 by 0.6319 with the each and every element. So it will become, see, 1 by 0.6319 into, if you go for adding up all these elements in the first row, it will become 456.91. The second row, if you go for adding up, then it will become 529.55. And the third row, if you go for multiply, then add, then it will become 407.43. Now we are going to multiply these two. So it will become, see, x1 is equal to 723.07, x2 is equal to 838.02, and x3 is equal to 644.77. What it means? See, this is the new sectorial output. This is the new sectorial output which is required to produce if the final demand is increased to 400, 500 and 350 respectively in the particular. So this is the final demand vector. So this is the final output, that is new sectoral output, that is x1 is equal to 723.07, x2 is equal to 838.02 and x3 is equal to 644.77. What it is showing that? It is the new sectoral output if the final demand is going to increase to 400, 500 and 350 respectively in each sectors. So this will be the new sectorial output. Now we are going to consider another problem, that is problem 2. Determine the total demand for industry 1, 2, 3 given the matrix of the technical coefficient of A and the final demand vector D. See, what is the technical coefficient given here? This technical coefficient matrix, that is A is equal to 0.2, 0.3, 0.2, 0.4, 0.1, 0.3, 0.3, 0.5 and 0.2. And the final demand vector is also given 150, 200, 210. What we want to find out? We want to determine the total demand for industry 1, 2 and 3. So of course, we have the given question. First, we want to find out the difference between identity matrix and the original coefficient matrix. So I am introducing here the identity matrix. It is 3 by 3 matrix. So the identity matrix minus the coefficient matrix. If you go for subtracting the identity matrix, the coefficient matrix from the identity matrix, then it will become 0.8 minus 0.3 minus 0.2 minus 0.4 plus 0.9 minus 0.3 minus 0.3 minus 0.5 and 0.8. So this is actually 1 minus A, that means identity matrix, the coefficient matrix. Then we have to find the determinant of the given matrix. So of course, you know how to find the determinant of the given matrix. See, here the determinant is equal to taking the first element, that is 0.8 into crossing the first column and the first row, then multiplying 0.9 into 0.8, which is equal to 0.72 minus 0.3 into minus 0.5, which is equal to 0.15, then minus 0.3 into crossing the second row column and the first row, it will become 0.4 into 0.8, which is equal to minus 0.32 minus 0.3 into minus 0.3, which is equal to 0.09 minus the third element, that is 0.2 into crossing the first row and the third column, it will become minus 0.4 into 0.5, which is equal to 0.2 minus 0.9 into minus 0.3, which is equal to minus 0.27. So if you go for simplifying it, the determinant value will become 0.239. So this is the determinant value. See, here the Hawking-Simon conditions are satisfied because the first condition, that all the diagonal elements should be positive. So it is 0.8, 0.9 and 0.8 here. So we can say that the first condition is satisfied, all the diagonal elements are positive. Then the second condition was, see, the determinant value is greater than 0. So it is 0.239. Of course, it is greater than 0. So it is a non-singular matrix. So the both conditions are satisfied. So we can say that Hawking-Simon condition is satisfied by the given matrix. And this showing that if the Hawking-Simon conditions are satisfied and the determinant value is greater than 0, we can find that it is a non-singular matrix, and accordingly we can go for finding the inverse of given matrix. So here we are going to find the inverse. Before that, see, we want to find out the minors and the cofactors. So here the minors are written, that is M11 which is equal to 0.57, M12 which is equal to minus 0.41, M13 is equal to 0.47, M21 which is equal to minus 0.34, M22 which is equal to 0.58, M23 which is equal to minus 0.49, M31 which is equal to 0.27, and M32 which is equal to minus 32, and M33 which is equal to 0.60. Now, after finding the minors, we can go for calculate the cofactors. See, the cofactors we can find from this particular minor. Corresponding to the each minors, we will have a cofactors as well. So I am writing here the cofactor 1, that is C11 which is equal to minus 1 raised to the power 1 plus 1 which is equal to minus 1 square, which is equal to 1 into the first minor which is equal to 0.57 which is equal to 0.57. Similarly, C12 which is equal to minus 1 raised to the power 1 plus 2 which is equal to minus 1 cube which is equal to minus 1 into the second minor which is equal to minus 41. So here if you go for multiplying, minus will become plus, so it is 0.41. Similarly, the third cofactor which is equal to 0.47, then C21 which is equal to 0.34, C22 0.57, cofactor 23 which is equal to 0.49, the C31 which is equal to 0.27, C32 which is equal to 0.32, and C33 which is equal to 0.60. See, we are calculated the 9 cofactors as well corresponding to the each minors. So I am writing the cofactors separately here: C11, C12, C13, C21, C22, C23, C31, C32, and C33. We have the 9 cofactors as well. By using these cofactors, I am going to write the cofactor matrix here. So cofactor matrix, we are going to replace the original matrix by using the cofactor elements here. So it will become, see, cofactor matrix is equal to 0.57, 0.41, 0.47, 0.34, 0.58, 0.49, 0.27, 0.32, and 0.60. After finding the cofactor matrix, we can go for finding the adjoint matrix by interchanging the rows into the columns. That means we are going to take the transpose of cofactor matrix. So after the cofactor matrix transpose here, we are going to consider the first row will become the first column here, the second row will become the second column here, and the third row will become the third column here. See, this is the adjoint matrix. See, after finding the adjoint matrix, we can go for calculating the inverse. So here the inverse is equal to 1 by the determinant value is equal to 0.239 into the adjoint matrix here. So here, after finding the inverse, see, we are going to multiply the final demand vector, that is D. See, final demand vector I have written here separately, 150, 200 and 210. We are going to multiply the adjoint matrix with the final demand vector D. We have a 3 by 3 matrix. Adjoint matrix is a 3 by 3 matrix, and we have the demand vector which is equal to 3 by 1 matrix. Of course, the matrix multiplication is possible, and if you multiply these two matrices, then it will produce a 3 by 1 matrix. So we are going to multiply these two matrices, then it will become, see, 0.57 into 150 plus 0.34 into 200 plus 0.27 into 210. Then it will become 210.2. Similarly, the second row we are going to multiply with the final demand vector, then it will become 0.41 into 150 plus 0.58 into 200 plus 0.32 into 210. Then if you go for simplify it, then it will become 244.7. Now we are going to consider the third row and multiply with the final demand vector. So it will become 0.47 into 150 plus 0.49 into 200 plus 0.60 into 210. If you go for simplifying it, then it will become 294.5. Now we are going to multiply 1 by 0.239 into every element of the column vector here. See, if you go for multiply it, then it will produce, see, 879.5, 1023.85, 1232.22. See, this is the final output. See, final output, that is x1 is equal to, here it is 879.5, x2 is equal to 1023.85, and x3 is equal to 1232.22. So after this, see, we want to determine what happen if new level of total demand, that is if the final demand is not increased to, but it is increased by 40 in the industry 1, 20 in the industry 2, and 25 in the industry 3. So here we are going to replace the final demand vector by using this particular equation, that is changed output now is equal to the inverse into changed final demand vector. So I am applying here, see, it will become the inverse, that is 1 by determinant value into the adjoint matrix into, now the changed final demand vector, now I am substituting, it is 40 in the industry 1, 20 in the industry 2, and 25 in the industry 3. So I am writing the final demand vector, new final demand vector is equal to 40, 20 and 25. And if you go for multiplying these two matrices, then it will become, see, it is 36.35, then 36, 43.60, and if you go for multiplying 1 by 0.239 into 36.35, then it is equal to 152.09. Then similarly, 1 by, that means 36 divided by 0.239, which is equal to 150.63, and 43.60 divided by 0.239, then it is equal to 182.43. So this is the changed output. That means if the final demand is increased by 40, 20 and 25, then the final output will change to 152.09, 150.63, 182.43. Now the new output, that is the old one, that is old output plus the increased or changed output, it will become, the old one was, we are already estimated in the last slide, see, it is 879.5, 1023.85, 1232.22 plus the new output, that is 152.09, 150.63 and 182.43. Now if you go for adding this, then 879.5 plus 152.9, which is equal to 1031.59, then 1023.85 into 150.63, which is equal to 1174.78, then 1232.22 plus 182.43, which is equal to 1414.65. So this is the new output. This is the new output, that is if the total demand, that is if the final demand is increased by 40 in the industry 1 and 20 in the industry 2 and 25 in the industry 3, then the final demand, that means the final output which is required to produce by the industry 1, which is equal to 1031.59, industry 2, which is 1174.48, and the industry 3, that is 1414.65. So let me conclude here. I hope you clear about how to find the total output, intermediate demand, final demand, and number of labor days required. Then the changing total output of the each industry when the final demand is going to change. So we will see in the next lecture. Thank you.